Alright, so welcome back. Hopefully you guys have had a chance to fill this out and take a look. We'll go ahead and let me show you. Let's see. So for n is 2, then our degrees of freedom, just so we're clear about this all, degrees of freedom would be n minus 1. So that would be 1 in this case, right? Because 2 minus 1 would be 1. So if we kind of look at our table, and again, let's see, confidence interval 95%. We're going to look at this column here, and n is 1. So n degrees of freedom, sorry, n is 2, degrees of freedom is 1. We look at this row here, so it looks like it's 12.706. That's what we're looking for. So 12.706 would be this one, 12.706. And then for n equals 11, again, degrees of freedom would be n minus 1. So that would be 11 minus 1, so that would be 10. So we look at our table, this one. So again, this column, and degrees of freedom 10, right through here, 2.228. So that one should be 2.228. And if you have gotten those incorrect because you weren't quite sure how to figure this out, then just adjust now and fix and pause this and find the other two. So I'll go ahead and move on. N is 61, so that means that my degrees of freedom would be 60. So here's 60, and we go out, and it's right here, 2.00. 2.00. And then the last one, and we talked about this before, right? If I'm at 120, between 120 and 500, 126 is far closer to 120. And in general, you always want to round down anyways, because rounding up, you're going to take something too large, so it's always better to be safer and round down. So even if it was 100 and, even if it was, kind of in the middle, like, it was, say, 300, you still should round down to 120. Take the kind of the larger number just to be safe. So 1.980 is what we're looking at here. So this one is 1.98. Whoops, this is very, very annoying. 980. So you kind of look, as we kind of go down, you can see that as n gets larger and larger, in the beginning, if your sample size is 2, then really the odds of your standard deviation being good is really, really unlikely, right? It's just going to be crazy. But if you get an n of 11, it starts becoming a lot better, significantly better, right? This is much closer. This is if it's perfect, 1.96. You can see this is a lot closer to that. And then as your n gets larger and larger, then your t gets closer and closer to 1.96. And finally, when n is infinity, it actually is 1.96. So, really what this is saying that if it's a sample, then, especially when you have small samples, then your standard deviation is going to be likely to be really, really messed up. So you need to have a really big t-score to kind of adjust for that. And as your n gets better and better, larger and larger, then your standard deviation is more and more likely to be closer to the real standard deviation. So the kind of the little extra you need to give to adjust for that can get smaller and smaller. So it ends up being eventually the same z-score as what you started off for. You have less room for error you need to have. So it's important that you kind of note that and kind of realize that. Let me go ahead and skip back to here. There are some characteristics, right? It differs from the standard normal distribution in a few different ways. One, the variance is greater than 1. It's actually, the t-distribution is actually a family of curves, so every single curve, I think I have them below that, is a different degree of freedom. So it's kind of every single, if you kind of look at this sheet, every single one of these represents a different curve. And if you kind of look at the very, very bottom down here, the z-scores, you'll see that really the z-table is much bigger than just these 7 scores down here. But we've taken kind of the most popular z-scores off of that z-table and just summarized them into this table. That whole table, we just grabbed the 7 that we need from that table. And so each one of these different n's, degrees of freedom, is its own curve, its own set of numbers, and kind of we've grabbed the important ones from there. And then, as we talked about a second ago, as the sample size increases, the t-distribution approaches a standard normal. It just gets closer and closer. So we'll take a look at some curves here. I'll show you what I'm talking about. Right, so it's basically every n has a different curve that kind of starts off kind of more flat, but as your n gets closer and closer to infinity, then it becomes closer and closer to the real normal distribution curve. And like I said, each one of these curves, it would sort of have its own whole table, but we've just summarized them just to these 7 numbers that we need, that we care about in terms of critical values, because we really only care about, we don't take confidence intervals of 96.37%. We only care about the basic ones, 90%, 95%, stuff like that. Oops. Okay, so go ahead and do problem 7 on your lab. Find the t-value for n is 18 for the 99% confidence interval for the mean. So go ahead and pause this video here and go ahead and look that up. So pause now. Okay, you should be back, and we're looking at n is 18. So when n is 18, my degrees of freedom is equal to n minus 1. So that's equal to 18 minus 1, so 17. And we're taking at a 99% confidence interval. So I'm going to go over here and take a look. 99% confidence interval. So confidence interval is this top part here. 99%, that's there. And degrees of freedom, 17. So I'm going to slide down to 17, and there it is. 2898. 2898. That's what we're looking for. So that would be our t-value. That would be our critical value. So think of it like that. The critical value we're going to use is 2.898. All right, so here's some notation for you. Again, mu or mu naught, that's our population mean, the thing you're trying to estimate or trying to guess at. Remember, estimate is the same thing as saying find the confidence interval. So if I ever say estimate, that's your clue that the problem is a chapter 7 problem. It's the same thing as find the confidence interval. So confidence interval and estimate mean the same exact thing. So what are we trying to estimate? The population mean, mu or mu naught. What are we trying to estimate it with? The sample mean, x bar. Sample mean, the mean we get over sample, that's our best guess for the population mean. It's our best point estimate, x bar. And then S is our sample standard deviation. N is our sample size, the number of numbers. E is our margin of error. And our critical value, which we're going to use CV, critical value, is our t-score. So it's the number we get from our t-table. All right, so here's the procedure. Same as all the other ones. You take the mean plus or minus your error. So in this case, our mean is x bar plus or minus our error, where our error is our critical value. I'm going to actually erase this, block that out, and make this a little more consistent, and call that our critical value. So our critical value times S over square root of n. So here I need, right, in order to do x bar minus e to x bar plus e, I need my x bar, which we have. I need my error, which you find by finding your critical value from your confidence level, and then your standard deviation divided by square root of n. And again, your critical value is going to be from using your t-table. Here is our example. A common claim is that garlic lowers the cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. The changes in their levels of LDL cholesterol have a mean of 0.4, standard deviation of 21.0. Using the sample statistics of n is 49, x bar is 0.4, and s is 21.0, construct a 95% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. What does that suggest about the effectiveness? So, again, how many were selected? You had 49 subjects. That's your n. They had a mean of 0.04. That is your sample mean, x bar. It's from a sample, and this is your sample standard deviation. So this is your s. So we're going to find our error. So first of all, our error is equal to our critical value times s over square root of n, and our critical value from the table. So let's see, our n is 49, so that means my degrees of freedom is equal to n minus 1, 49 minus 1, so that's 48. So you're going to bust out your table and say, wait, what is this, 95% confidence interval? So we need that also. So 95% confidence interval, we need 48. We don't have 48, so the best we have is 40. Got to round down to 40. Again, you always kind of want to round down. So 2.021 is what we're going to use. So my critical value, 2.021. So then my error is going to be 2.021 times s. My s was 21.0 over square root of n, which is 49. Okay, so then that's going to be, I think I'm out of space here. So that's going to be 2.021 times 3, square root of 9 is 7, 21, I did the division already, 21 over 7, so it's going to be 6 point, oops, this becomes just 21 over 7 is 3, so 3 times 22.021 is 6.0, it's a terrible O, 6, 3. Perfect, so that's my error. So I'm going to do my whole x bar plus or minus my error. So my lower limit is going to be x bar minus my error. My x bar was 0.4. 0.4 minus 6.063, comma, my upper limit, which is going to be 0.4 plus 6.063. That's my confidence interval there, which will end up being negative 5.663 to 6.463. And that is my confidence level. And you might say, well, why is this so small and this so big? It's because we're looking at the difference. So the difference should be close to 0. So how much does your garlic level change? And your garlic level should change about, not at all, about 0. So it's saying that, if you look at your cholesterol level before and after. It might change and go down as much as 5.6, or it might go up as much as 6.46. So it might, it'll go up or down about this, somewhere in this range. So what does it say about the effectiveness of garlic in reducing it? Not much. In fact, my mean was even positive, but it could have gone down, it could have gone up. It really doesn't really seem to indicate a whole lot of effectiveness in that. Here it is prettier if you kind of want to look at the nicer sort of numbers here that they've got. They got a slightly different, oh, they had a little bit nicer T, I guess. Because they had a 50, and we didn't have 50 in our table, so they have a slightly different answer than we do. And then again, here is their kind of more final answer, and has kind of a nicer little talks about it a little bit more. So if you want to go ahead and read through that, you can go ahead and pause this now, and go ahead and read that if you like. Okay, so we're going to go ahead and move on. Lab problem 8. So you guys go ahead and do this one. Again, don't forget you need to find your degrees of freedom. You need to figure out what your N is. Figure out from there what your degrees of freedom is. And then you should figure out what your confidence level is. So then you can figure out what your, use that and your degrees of freedom to figure out what your critical value is. And then you're also going to need to figure out what your X bar is, and you need to know what your S is. You need to find all those different things. Oh, and your, yeah, that's everything. So go ahead and find those, and maybe we'll check back when you found those to kind of make sure you're on the right page before we go ahead and move on and give you a few more minutes to solve the problem. You find your E and your confidence interval. So find those and then come back. So pause this until you find those. Okay, so your N, sample of, remember that's your key. So sample of 10, that's your N. N is 10, which my degrees of freedom is 9. It's going to be 10 minus 1. My confidence level is 95% confidence interval, so 95%. Means I'm going to pull out my table again. Degrees of freedom 9, confidence level of 95. So again, our 95% confidence level, we're going to go down to degrees of freedom 9, 2.262 right here, 2.262. And then my X bar, sample mean. Let's see, average, random sample, found the average growth. So this is your sample average, or sample mean, was 9.8. And then assume the variable, blah, blah, and the sample standard deviation is 0.96. Okay, so now you have all the pieces. Go ahead and pause this, find your error, and find your confidence interval. And come back when you're done, finding those. Okay, so your error is equal to your critical value times S over square root of N, and that is your critical value, 2.262 times S, 0.96 over square root of 10, and go ahead and I'm sure you've calculated that. I did not yet. That's kind of my problem. And I got 0.68669, so I'm just going to round that out to 7. All right, so then we have our X bar plus or minus our error. So that's going to be X bar 9.8 minus 0.687 to 9.8 Seems really small. I guess no, I guess not. Plus 0.687. So we'll end up with 9.1 around 9 yep, to 10.49. And actually that probably rounding off to 9.1 to 10.5. So that would be your confidence interval. And oh, actually they don't round. Okay, so yes, so this is kind of what they got. This is it prettier if you want to see that. And then they kind of give a nice summary saying that one can be 95% confident. The population mean in the first year growth is between 9.1 and 9.11 and 10.49. So we're saying that that's our confidence level that the population mean really is in this range here. All right, and then this is exactly the same as what we did with the proportions. If we want to guess what our point estimate is, in other words, our x bar, we would take, if we have a confidence interval, right? So the last one we had was 9.11 to 10.49 or something like that. So if we have this and we'll figure out what our best point estimate is, in other words, what our x bar is, our best guess is, we know it's smack dab in the middle of these two. So if we take those two, we can add them, we can average them, add them up, divide by 2, because there's 2 of them, and we can get our best point estimate, our x bar. And we also know that our margin of error from these, it's from this spot to this spot, it's 2, this goes, to the middle, to x bar, and then back out to this one. This is an error. This is another error. So we know it's two errors to get from here to here. So we can just subtract them, take this one, subtract that one, divide by 2 to get our error. Or you could just, once you find the x bar, you can just subtract that from this, or take it and subtract this one to find the error as well. You can do it that way as well. Same exact thing as we did with the proportions. Here is just another comment on how we might find the sample size for estimating a population mean. So this is, again, similar to what we did with the proportions. If we have an error, you want it to be within so many, so many inches or within so many feet or whatever it is. You can fix your error, right? The within, the plus or minus, you can fix that, and then you would solve for, so my error is equal to my critical value times s over square root of n. And if I wanted to figure out what my e was, or solve for n, I would square both sides. So then I would end up getting e squared times our critical value squared times s over, and this would just go away. And then I would just multiply both sides by n and divide both sides by e squared. So then these guys would go away, and those guys would go away, and you're left with n is equal to the critical value squared times s squared over e squared, and that's what you've got. This is your critical value. Well, the whole thing squared, so they just did, actually they used, sorry, my bad. We only do this with mu and sigma, so this actually is sigma, which is why we rarely ever do it. So this is my critical value squared, sigma squared, e squared, or you can just multiply them first and then square all of them together, which is what they did. And that's one of the issues, is that you have to know what your sigma is. And in order to do that, you have to, because you can't figure out what you can't use a critical value of the t-table because you have no idea what n is. So you have to use a z-table, which means you have to kind of guess what sigma would be. So it's usually kind of not so accurate. And you have to sort of guess at what sigma might be. And these are some different ways of doing it, which are all kind of bad. You can use that range rule of thumb and say, oh, it's about four standard deviations from the top to the bottom, your range. So that's not a good way of doing it necessarily. You can start taking a sample, right? And from your sample, you can kind of estimate what the standard deviation of that sample, which again is going to be not very accurate because it's going to be a fairly small n. Or you can use a previous study, but again, none of those are really all that great. So we're really not going to emphasize that in this class, but yeah, I just kind of wanted to point that out and briefly go out over that. Incidentally, in general, we are never going to use this stuff we used here. Where we know what our population mean is and we use sigma, because you never ever, we'll go back to this part. Where was it? Nope. Nah. Help me. There we go. We pretty much never ever ever know our sigma, and we don't know our mu. So pretty much we're never going to use that method at all. Where we have this whole sigma over square root of n and a regular critical value. We're never going to do that. We're always going to have, if we're talking about a mean, it's always going to be a t-table. So a mean means a t-table. Let me actually put that out here. Mean, use a t-table. So what I tell my students is, think of mean Mr. T, right? Mr. T isn't mean, but he looks mean. So mean Mr. T, if you have a mean, you're going to use a t-table because you're going to use S. If you use a proportion, then you're going to use a z-table. And like one of my students said, he remembers it by saying, just think of easy peasy, right? Easy peasy, easy peasy. You have a proportion, you use a z-table. Mean Mr. T, you have a mean, use a t-table. So that's just kind of the way that you sort of think about these things. So mean Mr. T, mean, use a t-table. Easy peasy, p, use a z-table. Just try to think about that and remember that. That's just a good way of kind of keeping track of these things, because there's a lot of stuff that starts getting a little bit complicated now that we're kind of getting into some different things here. Okay, so here is an example, which, you know what, we're going to skip that because I don't think it's very important. I don't value this part of this very much. So what we're going to kind of do, this is, I think, at the bottom of your page. It's kind of the important part here is figuring out which distribution to use, because it gets a little bit confusing, just a little bit, and you really need to lock this part down and really know it well, because chapter 7 is not difficult. However, when you start mixing in chapter 8 with it, and you start having both of them kind of floating around your brain, then they start getting confusing. So you really need to get 7 down solid and really get a solid feel on it before you get to 8. So then 8 won't screw up your 7 in a sense. So here's the thing about 7. If it's a t-table, then you're looking at mean Mr. T, right? That's when you use the t-distribution. When you have a mean, x bar, you're trying to find a mean, then mean Mr. T, you use a t-distribution. That's when you have your data is numbers, right? This is a numerical data. And then we have a z-distribution. When do you use a z-distribution? Think easy peasy. It's when you have a p, when you have a sample proportion, right? You're looking for p naught. So these are proportions. Easy peasy. These are proportions. And these are going to be when you have a yes-no, a yes-no question, right? Yes-no data. Data is yeses and nos. So that's the thing. Got to really kind of make sure you lock that down. It's proportion when you have Your data is yeses and nos, so you're looking for either it is or it isn't. That's your question, the question that it came from. And then just think easy peasy. Proportion, you have a p hat, trying to find p naught, pz, z distribution. If you have numerical data, you have a mean, you have an x bar, you're trying to figure out what your mu is, your sample mean is. So think mean Mr. T, you're going to use a t distribution. Okay, so that is it for today. We're gonna kind of stop there. So hopefully you've got that settled in. Make sure you do your homework. I would say at least do 7.1 before the end of spring break, and then if you want to wait until that first day that we get back, when we have our first meeting together online, the Tuesday after spring break, then if you want to wait till then before you start your homework for 7.3, that's fine, but at least get that first one taken care of. All right, have a great spring break, and I will talk to you guys later. Take care.